Hello, everyone. My name is Brennan Hill from the University of Wisconsin-Madison. Today, I'm presenting Structural Plasticity's Active Inference, a biologically inspired architecture for homeostatic control. We're proposing an architecture that moves away from fixed topologies and global backpropagation in favor of local, self-organizing rules. Let's start with the key takeaways. We're introducing the Structurally Adaptive Predictive Inference Network, or SAPIN. SAPIN is a biologically inspired model where the processing cells, or the neurons of our network, physically migrate across a 2D grid. They move to minimize their own local prediction error. Crucially, this architecture demonstrates that the intrinsic drive for homeostasis, simply trying to keep internal state stable, is sufficient to solve control tasks like carpool without explicit reward signals. So why take this approach? The challenge with traditional deep learning is it relies on global backpropagation. While powerful, backpropagation is both biologically implausible and energy efficient because it requires perfect metric knowledge of the entire network and for the entire network to be updated at once. Instead, we look to the free energy principle. This theory posits that biological agents act to minimize surprise or expected prediction error to maintain homeostasis. We also draw inspiration from somatic computation and morphogenesis. In biology, cells physically reorganize themselves to solve anatomical problems like regenerating a limb, as well as to perform calculations. We asked if we could use the same structural plasticity to solve computational control problems. This represents a shift in methodology. In traditional reinforcement learning, the top row, an agent observes a state and selects an action to maximize reward. In the SAPIN model, or bottom row, the agent views actions as sampling the environment. Its goal is to minimize prediction error, or surprise. Let's look at how this works under the hood. Our network exists on a grid. In this environment, there are static input cells on the left in blue, static output cells on the right in red, and the rest are dynamic processing cells. Each processing cell has a current activation, V, and a learned expectation, E, its homeostatic set point. The learning happens in a dual loop architecture. First, there is synaptic plasticity, which happens every single time step. The cell calculates a local prediction error, the difference between its actual activation, V, and its expectation, E, then updates its internal expectation and its connection weights to reduce this error in the future. This is a local Hebbian-like rule. If a cell is surprised, it adjusts its weights to better predict the input next time. Sometimes weight updates aren't enough. This brings us to the second loop, structural plasticity. This occurs over a macro episode. If a cell is chronically surprised, means the long-term average error is high, it develops a desire to move. If it's overactivated, receiving too much signal, retreats away from the largest source. If it is underactivated, it approaches the largest source. This allows the network to dynamically optimize its own topology. You can see the grid in action. The pink lines in the cell represent propagation of signals. SAPIN uses an excitation-based order for propagation, where the most active cell fires next, allowing for flexible, data-driven pathways. The yellow cells represent those that have already fired this iteration. The green cells represent those that have not fired yet. An example of cell movement. Blue arrows show direction cells move to, while red arrows show directions they fail to move due to another cell already occupying the space. In the example depicted, exactly one cell will not move due to receiving signals nearest expectation and a total error less than the threshold, which is common early in training. There's an absolute chance that each cell moves in a random direction. Otherwise, it moves the direction that is most close to this expectation. We also test the punishment mechanism. Inspected by the red lines, random error is sent from random locations on the grid and is then used to update weights and movements. We tested this on the standard cartpole benchmark. The result is that SAPIN successfully solved the task using only this local error minimization. In addition, it turned out the error effect had no noticeable effect. However, the network seems to be relatively unstable and would often forget a good pause after discovering it. When we implemented a locking effect, the agent maintained an 82% success rate over succeeding episodes. This suggests a need for a consolidation phase in continuous learning systems. We've demonstrated a research direction approximating active inference where agents learn where to position resources, instead of just how to weigh them. The major implication is that homeostasis seeking is efficient objective function for these types of control tasks. For the future, we're looking at adding recurrent nodes to enable long-term planning. We're also exploring physical deformation, placing the cells directly on the pole or the cart itself, so their movement changes the physical environment. Finally, moving from a discrete grid to continuous space to stabilize movements. We're currently working on V2. We've implemented this continuous space to stabilize movements, in addition to a cylindrical topology to avoid bias towards central inputs and outputs. Instead of choosing a discrete cardinal direction, the cell in V2 calculates a continuous movement vector based on the weighted sum of its inputs and internal expectations. It then samples from a quadrilateral to probabilistically determine a drift direction from calculated desires in all directions. Thank you for your time. If you're interested in the full paper, please scan the QR code here.